Good afternoon, and welcome to the Daylight Symposium stage here in Copenhagen. And it's a pleasure to have you joining us for day 2 of the Build for Life Daylight Symposium. It's the 9th symposium that's been taking place, and I have to tell you, every year it gets more and more exciting. And I want to thank those of you who joined us yesterday and promise that today will be very inspiring and interesting as we have a great lineup. We have 3 subjects in 3 sessions today here in Copenhagen. One is on the pandemic, and what have we learned from this time for the last year and a half, these new living conditions, and what will happen in the future. We also have a session on computational design, and we'll be looking at the democratization of computation and new tools in architecture. And finally, we'll drill deep into glare and controls, and that has to do with daylight and windows. Now remember, if you have questions, please use your chat. Feel free to write your questions because we will take them in our Q&A period at the end of each session. And for those of you who prefer a language other than English, please go to the top right of your computer screen and you'll see an area called Interprify. And if you go down, you can select from the menu the language of choice. But don't forget to turn down the English volume in your video recorder on your player. Now, our first speaker, you may have noticed that Kevin is not with me moderating this morning, but don't worry, he hasn't jumped ship, he is here, and Kevin is our first presenter. Kevin Wymelenberg is professor at the University of Oregon, and he directs the Institute for Health in the Built Environment. Now, this institution seeks to facilitate the integration and a holistic approach among a broad network of researchers and academics, and they're interested in the fields of health, comfort, and sustainability in the human ecosystem. Please help me in welcoming Kevin Wymelenberg.
Well, thank you, Martha, and it's fun to be joining you in this new role. This topic is, of course, at the Build for Life conference, but I'm a little worried because my presentation is all about death, but maybe it'll be about emerging life through death. I'm going to be sharing with you some research that we've been conducting over the last year or year and a half about the role of daylight in the indoor environment to shape the indoor microbiome. And a few years ago, I guess 2 years ago, at the 8th symposium, I shared a little bit, and you'll see one slide of that, but I'm going to focus today on the role of indoor daylighting, UVA, UVB, and visible light in mitigating indoor viral pathogens. We'll focus specifically on SARS-CoV-2, which is the virus that causes COVID-19, but I think a lot of these principles are can be broadly understood. And just trying to get the slides to advance. There we are. Quick disclaimer, I have to do this in every presentation I give. Since the pandemic started, I've been doing some work outside of the university, and below at the disclaimer at the bottom describes it. Basically anything where the insurance profile is a little too complicated for the university, I'm now doing some private consulting. So something related to indoor pathogens, and I can do research at the university, but if it's more of a consulting role, I do that through a private company called Ductal. Okay, and this is a little bit about the team. I'm going to skip quickly through it, but needless to say, there are a lot of individuals who supported and created the development of this work. All right, this is the really quick summary from last symposium. And it just is here to say that we know that the indoor environment, daylight in the indoor environment, invisible light indoors, indeed shapes the indoor microbiome. This particular study was looking at the difference between bacteria communities in dust versus under no light versus light, visible light, and ultraviolet light. And you can see there are some distinct species differences, in particular Saccharopolyspora being most dominant in the dark communities and nearly absent from either of the light communities. But the question then becomes, well, what about the pandemic and the virus? So this was about bacteria, so what about the virus? And early in the pandemic, we put this visualization together, which has been used to describe the distribution of pathogens in the indoor environment. It should be playing, so I don't know why it's not, but maybe it will start soon. And it basically just walks through the sort of way that viruses are expelled from our bodies and then move through the built environment, in this case being caught up in air circulation systems. And I'm going to give it one more shot to play, and then I'll just move on. Okay. Anyway, you can find the link online. There's a YouTube channel, and it will show the virus moving around the Guangzhou restaurant in China. Okay, so more to sort of Build for Life and Daylight Symposium. Now what? So there's some research that was available early in the pandemic about the survivability of pathogens on surfaces. And this is SARS-1 and SARS-2, SARS-2 being the virus that causes COVID. And you can see that in steel, it lasts, viability remains viable, can cause infections for about 13 hours, and in aerosols for about 3 hours. And a couple of months later, a new study came out that showed quite a different result, whereas it could last nearly 6 days in steel. And the question that I was asking, what's the difference between these two studies? And the answer, of course, is light. And that in the second study, it was conducted in a completely dark environment. So the first study, which was the one that everyone cited, was under normal, whatever normal lighting conditions are. And of course, they weren't characterized or described. But if we want to understand the role of light in mitigating pathogens, we need to understand it without light and with light. So there are a few studies that look in particular at specific wavelengths. And in this case, we're looking at viral inactivation using UVB. And you can see the plots show different intensities of UVB and how quickly the virus will become inactivated. And it's as quick as 6 minutes or 12 minutes, depending on the intensity of UVB. And this is what that looks like. And I'm going to show you this quickly and then kind of summarize it. But this is minutes up the vertical axis and intensity over time across the horizontal axis. And it's meant to sort of collect the area under the curve as the degradation potential of the UVB. And then, of course, we are thinking about daylight in buildings, and so we care a lot about visible light as well. And what we're seeing here in this slide is the visible light's impact on viral degradation. And this is the curve. And it looks really similar. However, the caveat is that it's in hours on the vertical axis as opposed to minutes. So visible light does not have the same potency to inactivate virus as UVB. And this is the kind of similarity between, or the relationship between the two. And what you can see here is that visible light is 263 times less capable at inactivating the virus, which sounds incredibly difficult and insurmountable, and thinks, well, then maybe there's just no story about what happens in the indoor space. However, as many of you probably are aware, our glazing products typically filter out nearly all the UVB and also nearly all the UVA. But about 0.5% of the outdoor UVB that exists in the atmosphere does come through many of our common glazing products. And so the answer isn't zero. And what's interesting is that 0.5% means that difference between visible light and ultraviolet light of about 250 times makes them a little bit more on even keel or on par with one another in terms of actually inactivating the virus. So it's important to look at both. So this is the quick summary of the workflow that we went through, and Alan Mahich and Isaac and Yvonne and others on our team helped put together. the thing that you need to have as a starting point is a really good understanding of the terrestrial spectrally resolved data, and we happen to have a wonderful solar monitoring station at University of Oregon that we can use and get wavelength-specific intensity measurements of the outdoor environment. And so we were looking in particular at the UVB range from 280 to 315 nanometers, and then we worked through the physical model to understand a digital and physical model, but we put in parameters of the appropriate reflections of the UVB spectrum, which are of course different than the reflections of UVA and daylight, visible light. And then we modeled the sky dome, and basically we hacked radiance to run this wavelength and accumulate the power over time and estimate the viral degradation capability. So we also used some specific glazing products, and those are shown here. You can see the UVB. It looks like it's flatline. It's not. There's about 0.5% of transmission of UVB through these glazing products, and then there's a little bit more UVA, and then of course they're optimized in visible light. We modeled two spaces that I'm going to show you. One is this open office environment, and it's got skylights and north-facing glazing, and then another, and you'll just have to pretend that once this slide advances, hopefully not 6 slides, but once, that this is a south-facing window, and I will show you what the implication of a south-facing window in this small private office might look like. So just to kind of get your bearings, what I'll show you is the collected UVB spectrum that lands on a surface in watts per meter squared. And I picked the desk just to pick a small area. And so you can see time step by time step, what we did was accumulate the UVB intensity in watts per meter squared on this surface. And then we put it through the normal simulation paces. And this is important to get a little bit of wayfinding and how this slide works. And so in this top row is windows closed, and that literally means the hopper window is closed, and then the bottom row, it's windows open. And then I'm just trying to get a proof of principle here. And so the first would be 100% of the UVB is coming through. So what you'll notice when I hit play is that the windows open and the windows closed look very, very similar. And then there's a 5% and a 1% bucket. And just remember that it's a 0.5% that actually comes through. So this is a typical day in August, and you can see assuming that that surface was uniformly covered in the virus, which it probably wouldn't be, but just assuming that the surface was uniformly covered in the virus, this would be the degradation potential from UVB only. And we're showing it and characterizing the difference between the hopper windows being closed on the top and the hopper windows being open on the bottom, which is why you're seeing a differentiation of the degradation on the desk. And then to get a sense of scale, the blue and then black colors mean more degradation. And once it's black, it means it's been 100% degraded. But of course, this is SARS-CoV-2, and we therefore care a lot about aerosol transmission and not just surfaces. So we'll get to that. But before we do, we're going to show a zoom in and say, okay, it's also not just UVB that makes a difference. So here we have no light in the top and 0.05, excuse me, I said 0.5%, but 0.05% UVB, and then 68% visible light. And then over here, we have just the 0.05% UVB with windows closed, and then we have the accumulation, maybe a real world. These two are more real world scenarios, 0.05%, 68% visible light, and windows open. And what you'll see here is that that degradation has a pretty stark difference between when the windows are open, because you're getting the UVB coming through without the filtration, the selective filtering, and then of course the visible light in combination with the UVB is also quite substantial compared to just the UVB alone. Now note, none of these simulations are including the UVA, and that is because we don't have any data available for the degradation potential of the virus from UVA. If we did, I would imagine it would be performing somewhere between UVA, or excuse me, between the potential, the power from UVB and visible light. So this, if anything, I would say is an underestimation of the degradation potential from daylight and UVB only. Okay, so this is the transition where it's important to say, well, we don't care so much about surfaces, but we definitely care about the breathing plane and the air within the space. And so we're using, in this case, no light and the aerosol degradation. There is no strong data for aerosol degradation. So in the top right or top left corner, we're assuming no light and aerosol degradation of something between the Van Dormelen paper at the first paper I showed and the second paper I showed when I was talking about steel. We made some estimates to get an approximate aerosol-based degradation under no light conditions. And then you'll see a pretty similar layout. And then finally, in the top right corner, you'll see a summation of the total degradation potential of each of those conditions. And this is specifically looking at the breathing plane. So as this video plays, you'll start to see the differences. Oops. It looks like the folks in the back room are going to have to run this video because it doesn't seem to be playing. There we go. Give it one more go. There we go. Thank you. So it's starting to shift color, you'll see, and then finally in the bottom right-hand corner, we are getting some full elimination of the virus within the zone. And the combination of the UVB, the visible light, and then of course the windows open where the UV can penetrate directly, compared to the top where the windows are closed and the UVB is being filtered by the glass. All right, one more set, and I think this video set will play automatically. And this is kind of taking it from the small scale space to the large scale space, the open office environment here with skylights. And as this one kind of nears the end of its duration, you can see something in the neighborhood of 40 to 65% degradation potential of the virus that may be in the breathing zone within the space. And I think it's important to put a couple of caveats on this. Of course, if the windows are open, you're also getting fresh air, which is going to probably overwhelm the removal potential, but not from degradation, but just from removing it and diluting it, right? And of course, the layers of mitigation strategies work together. It also begs the question, why are we eliminating all the UVA and all the UVB? And I know there are several reasons, but one of those reasons is because it has degradation for not just virus, but it might erode synthetic materials and artwork and various colors and pigments, fabrics and whatnot. But I would argue that in a lot of our indoor environments, spaces with a lot of wood or other natural materials and metals or stones and bricks, they actually age more beautifully with the admission of some UVA and UVB. And so it does beg the question, maybe we should be thinking a little bit differently, maybe not in all spaces, but in some spaces, about allowing a little bit more of that ultraviolet spectrum in. There's some other research that would support that notion with regards to synthesis of vitamin D. And to the extent that we're eliminating nearly all the UVA and UVB because we're putting maybe not so high quality materials in our indoor environments, we could be creating a problem with some unintended consequences. But regardless, good daylighting, as you can see in the images on the right, has a substantial degradation potential just from the visible spectrum alone, even if we don't entertain those ideas of exploring some intentional admission of UVA or UVB. So I just want to end on this idea that daylight it's such an interesting design resource to use, because as I've studied it more over the years, I've just continually found deeper and deeper layers of meaning and potential with the inclusion of daylight from the sky or from the windows in our indoor environments. We know that daylight supports circadian regulation, and we learned about that yesterday. We know that access to views and nature support mental health and alertness. We know that access to views supports sort of alertness and stimulation and creativity. And we're also we've also become more aware of the role of daylight on the indoor microbiome, creating diverse microbiomes indoors that are not monocultures, and perhaps cultivating a garden of microbes that are supportive of human health. And then finally, we're learning today about the degradation potential of UVA, UVB, and visible light on pathogens in our indoor environments. And I think together, this is really thinking about daylighting as a broad support for human health in indoor environments. Thank you so much for your time.